Graphene skins turned a bird strike nightmare into a survivable event. Here is the problem with the headline. 60% higher impact resistance in a lab test does not translate to bird-proof at cruising altitude. That number comes from pristine samples struck under ideal angles. Real bird strikes are never ideal. They are oblique, they are off-center, and they hit at the worst possible angle for the laminate. A 2025 study on real composite rotor blades with titanium edging proved this exactly. When a bird hits at a large angle to the blade surface, the impact does not just compress the skin. It creates a shear wave that travels through the laminate, prying apart the fiber layers. Even with titanium reinforcement, those large angle strikes cause delamination and tearing. Graphene is remarkable at stopping a projectile that hits head-on. The nano sheets spread the force across their plane, dispersing energy incredibly fast. But a bird at 12,000 feet is not a bullet. It is a soft, deformable mass traveling at over 250 knots. It wraps around the leading edge. It does not punch through, it peels. And peeling exploits the weakest link, the interface between graphene and the polymer matrix. Here is what the graphene enthusiasts do not tell you. In a graphene-reinforced epoxy, the improvement comes from crack pinning and deflection at the nanoscale. The graphene sheets force a crack to twist and change plane, which absorbs more energy. But that only works when the crack propagates through the matrix. If the impact shear is strong enough to separate the graphene layer from the epoxy itself, that mechanism fails entirely. The real survivability in a bird strike does not come from the graphene coating. It comes from the architecture underneath. The multi-layered structure that alternates stiff graphene layers with softer, energy-absorbing interlayers. In patent filings for graphene aerogel composites, the design uses alternating layers where the graphene provides tensile strength and the aerogel disperses impact force in a broad cone. That nano interlock arrests micro cracks before they can run. Think of it like this. Graphene alone is a very strong sheet of paper. A bullet hits it and the sheet holds. But a bird at an angle does not just push, it drags. It creates a tearing force that pulls the sheet away from the glue holding it to the structure. The glue is the polymer matrix. And if the matrix fails, the graphene peels off like a decal. That is not bulletproof. That is a failure mode that lab impact tests rarely capture. Now add altitude. At 12,000 feet, the temperature is around minus 20 degrees Celsius. Graphene-modified composites change their behavior in cold conditions. The polymer matrix becomes more brittle. The coefficient of thermal expansion mismatch between graphene and epoxy creates residual stress. So the same impact that would cause a dent at sea level can cause a crack at altitude. The certification process for aerospace composites knows this. That is why no operational UAV with a graphene skin has undergone a formal bird strike test at 12,000 feet in any open record. The gap between lab-tested material strength and field-certified structural survival remains unbridged. Certification requires full-scale tests with real birds or ballistic gelatin projectiles at actual flight speeds and angles. And those tests are expensive. One European research project under the Graphene flagship did test graphene-reinforced composites for bird strike simulation. They used ballistic gelatin projectiles on an A350 horizontal stabilizer leading edge. The result? A 10% improvement in residual strength after impact. Not 60, 10. And that is with controlled, low-velocity impacts, not a full-speed encounter at 12,000 feet. That 10% is meaningful for maintenance and fatigue life. It means after a small strike, the part can stay on the wing longer before repair. But it is not the game changer that marketing materials suggest. It does not make the UAV invulnerable. It does not eliminate the risk of catastrophic failure from a large angle, high-speed bird strike. It just gives the engineer a slightly larger safety margin. Now consider the manufacturing reality. Graphene composites face serious challenges at scale. Uniform dispersion of nano sheets in the epoxy is difficult. They agglomerate. They create defects. And those defects become stress concentrators. In a bird strike, a stress concentrator is exactly where a crack will start. So a poorly manufactured graphene skin can be worse than a well-made carbon fiber one. the regulatory world has noticed. A 2025 study from the Graphene flagship Safe Graph project, published in the journal 2D Materials, identified critical safety and compliance gaps for graphene-enabled aerospace products. They pointed to exposure risks, environmental impact, and the lack of harmonized test standards. Until those standards are updated, any claim of bird-proof is premature. So where does that leave the UAV operator? The practical takeaway is this. A graphene-reinforced skin can improve resistance to small debris, hail, or low-speed strikes. It can reduce radar signature if designed with radar-absorbing properties. But for a 12,000-foot bird strike, the critical factor is not the material itself. It is the structural design that distributes the load, the matrix that holds the layers together, and the angle of impact. There is a reason the military tests with real birds or gelatin substitutes at full scale. They know that a lab coupon test does not predict field survival. They know that a 60% improvement in a flat panel does not mean a 60% improvement in a curved leading edge with rivet holes and access panels. The real world has seams, joints, and manufacturing flaws, and those are where failures start. If you want to make a UAV truly bird strike resistant at 12,000 feet, you do not just add graphene to the epoxy. You design a nano-interlock architecture, alternating stiff and compliant layers that arrest cracks, a tough matrix that does not become brittle in cold conditions, and a leading edge that deflects the bird away from the critical structure. The graphene is a contributor, not a savior. The 2025 composite rotor blade study with titanium edging is instructive. Even with a metal edge, the blades delaminated when the strike angle was large. The metal did not stop the shear wave from propagating through the composite. It just delayed the failure. That tells you that no single material, not titanium, not graphene, solves the bird strike problem alone. It is a system-level challenge. So the next time you see a headline about graphene making a UAV bulletproof or bird-proof, ask one question. Was that tested at 12,000 feet with a 4-pound bird at 250 knots at a 45-degree angle? If the answer is no, then what you have is a promising lab result, not a field-ready solution. The gap between the two is where real engineering lies. And real engineering does not rely on magic materials. That gap, between what a material can do in a lab and what it can survive in the air, is the difference between a press release and a certification. So the next time someone says graphene makes a UAV bird-proof, do not ask about the graphene. Ask about the test. Ask about the angle. Ask about 12,000 feet, because that is where the theory meets the sky.